you are losing a lot of value if you can't make it. There's an enormous return on investment for any company that's paying a developer a reasonable developer wage and sends their developers here. I can't tell you how big of a mistake it is not to send someone to CppCon.
Good afternoon, everyone, and welcome to Composable C++. Thank you for coming. My name is Ben. I do C++, and I try and make it composable. So, in this talk, I'm going to talk about composability in general terms with some case studies and some learnings extracted from them. I'm going to start out by defining what we mean by composability, and then I'll go through considering things at a fundamental level, so starting off with types and showing how composability of types moves into composability of higher level constructs, objects, and patterns, and then hierarchies and computation. And there'll be an interlude of compile time stuff in there as well. Do please ask questions as we go if you have any. I'll try to answer them, or I might have to hurry along at some points. You know how that goes with a talk. Anyway, first thing to ask ourselves, first thing I asked myself was, what do we mean by composable? We use words like reusable, flexible, extensible, composable, maybe even simple. Programming is really about breaking the problem down into parts that are small enough for us to understand and implement, and then taking those parts and recomposing them back together to solve the larger problem. And the first part normally goes okay, but that second part is where I always have problems. And those problems sometimes reflect back on our understanding of the first part. But really, that second part is all of programming. Composition is all of programming, really, so it's important to figure out what it means. Let me put that another way. This is the real problem of building software. When you're working on a problem, you never think about how beautiful it is, you just solve the problem. But then when you're done, you look around and the code isn't beautiful somehow. While you were working on the small parts, that was fine. Each of those can look like a gem on its own, right? But when you finish putting them together, you step back and it's a bit of a mess. You know, it's not always a massive mess, but there are definitely things in there that just don't look right. This quote really brought it home to me. This gives us the answer to what is composability. So, we debug software a lot. We get to understanding why it fails. The real thing is, why does it work? It's a very deep kind of question. So I thought about this for a long time. Here's the thesis I came up with for this talk. Software works because of properties we can reason about. And this is the root of composability. Alice writes some code. Alice gives that code to Bob, and Bob puts it to a use later on that Alice did not foresee when she wrote the code. And the code works. And the reason why it works is that Alice didn't have to foresee all the uses it would be put to. It works because it's composable and all those things as a direct result of Alice's understanding and principled basis for writing the code. So, I just need to say what composability is not. Composability in this view is not based on syntax. Good syntax is often mistaken for composability, particularly by people when they're talking about STL algorithms versus ranges. It can enable easy expression, but it's not the same thing as principled composability. We can't TDD our way into composability. TDD is for shaping the code and meeting requirements. Composability comes before the code, in a sense. Composability is not one particular pattern, and it's not in the domain of one particular paradigm. It's not functional programming only. It's not object orientation. It's not any particular paradigm. But it is this principal basis for writing our code. So one more time, composability is not about syntax. Now, 6 years ago now, Andrei Alexandrescu was on not this stage, but the stage in Bellevue in Washington, and he gave a great talk on allocators. Well, it was ostensibly about allocators, but when I watched it again, it spoke to me really about composition. And he said this, he said verbatim, if you want to design an allocator, you've got to make composition the first thing. Getting composition right is getting allocators right. And as I hope to convince you, it's really getting everything right. So let's start at the bottom. I'm going to start with the fundamentals, talking about types and functions. The most basic choice we have when trying to write composable code is choosing the return type of a function. And this is one of the most common errors I make in composability because I don't realize the choice I'm making when I make it. Because I'm working, again, on that small part code. I've broken down the problem, I'm working on the small thing, right? And I'm not thinking about the contextualization of the big thing. I'm not necessarily thinking about the composability. So I don't realize I have that choice, and that my choice at that level will affect everything above that. But the most simple thing I can do here, the simplest composable type, if you like, is bool. And, starting at the fundamentals, I'm omitting void because it offers no compositional choice, really. It only offers sort of temporal composition. But as I hope to convince you, it's incredible how much composition is built on the humble Boolean and the simple properties of it. In fact, as I was making this talk, I realized that most composable code, most patterns are built squarely on bool. So it's worth asking, why is bool composable? It's composable because we have several things we can do to put different Boolean values together. And already, this is very simple, very fundamental, but it already has structure arising from the fact that our function here is returning bool. A caller of our function can aggregate the results in several different ways. And whatever that true-false dichotomy means, and we get to define kind of the semantics of it for our function, it unlocks one level of composability of this function. And bool seems so trivial that we usually don't notice it. But lots of things build on the composability of bool. For example, obviously control flow. Almost all algorithms find all of, any of, mismatch, etc. Anytime we want to loop until some condition is true, we're exploiting those composable properties of bool. And that, it also underlies a lot of caching schemes, things like idempotent calculations, polling, and higher level patterns like chain of responsibility. So that composition, that loop that we think of in an algorithm can be over space, like over a collection, or over time in a poll, or over behavior, like a pattern. And I just want to make a note here that short-circuiting of and and or operators is a nice thing, but it's not fundamental to the composability of bool. So, whoops, back one. So here's the chain of responsibility pattern, for those that haven't seen it before. Basically, you have a request come in and you have several objects in a chain, and each object gets a chance to handle the request. And if it doesn't handle the request, then it returns something isomorphic to a bool. So it returns false, and then the next object in the chain gets a chance to handle that request. Until finally we're out of objects, and then the request goes unhandled. Maybe we raise an error. But at any stage, if an object does handle the request, then it would return something isomorphic to true. And you can see by this pattern that the pattern directly leverages the composability of bool, the humble bool, and the OR operation imbues the pattern with an inherent prioritization. That's really all the pattern is when laid bare. So I want to present another interface. This interface I presented back in 2018, and it's a putative logging interface. This is one interface that I used in real code, and it was very much in sort of early 2000s object orientation style. It's not really modern C++, so it's sort of classical object hierarchies with virtual functions. And the log sync, which is the thing that receives a log entry, really it has this one function interface. And crucially, that function returns bool. And that is the key to composability of this interface. Something it's quite a high-level concern, a cross-cutting concern, logging. But the fact that this returns a bool really unlocks the composability here. So given that one push function, we can write various log sync classes against that interface. Now, there are a couple of sort of obvious ones that don't really touch the bool aspect, and those are the syncs that just send the log to different places. For example, a file or a debug output window. We can write a sync that wraps another sync in an execution policy and does threading or deferred queue of logging or something like that. But the bool really kicks in when we consider filtration, filtering logs such that we might want to, I might want to tag every log in the sub part of my code with my name, and then when that log comes up, it's got my name on it, so so I get the error. We can write a predicate, a filtering sync. We can also write a sync that wraps several other syncs and either fans out the log entry to all of them, and it can stop at the first one that accepts it, very similar to chain of responsibility pattern, right? Or it can send it to all. And it can use and, or it can use or. And finally, and perhaps most importantly, we can write the null sync. The sync that just accepts every log entry you send it and does nothing and returns true. And logging is one of those things that we all have to deal with. And the sort of larger your application, the more control you want at compile time, at runtime. You want configuration and runtime. And this kind of thing gives you that composable nature. So bool is a very humble type, but it powers most of programming when I really look at it. Would you say, Jason? Okay, so let's go a bit beyond bool. Returning void, I said, gives no choice to the caller. Returning bool gives exactly one choice to the caller. So the natural question next is, what can be returned to give more choices to the caller, more composability? Int. Thank you, Jason. You haven't seen my slides. And when I say int here, I mean, actually, we might as well lump in with int any arbitrary arithmetic or numeric type. But I'm just saying int here for simplicity. So, and the slight spoiler here is that in some fundamental sense, bool and int are really the only two, or at least are isomorphic to the only two return types we need to unlock composability. So, why do we say int? Well, one trivial way of looking at int is that it's a collection of bools, and that's one way to look at it. But that's sometimes useful. But moreover, with int, we can say not just if something happened, if a log was accepted, but we can say how much of it happened, right? How much computation did we take care of? And when we go to bool to int like this, it opens the door a bit more for users of our function, which is ourselves 3 months, 6 months later, to layer on more behavior. Because if you can tell how much was taken care of rather than just if something was taken care of. So, and it allows incremental progress. If you have a function like this, which has the same, takes an int or takes a number and returns a number, you get to feed back its output into its input, and you get the composability of incremental progress. So there's a great example of this. Who's heard of steering behaviors? Only a couple of people. Okay. So Steering behaviors is a framework by Craig Reynolds. It's pretty old now. It's from the late 90s originally, I think. And the classic example is flocking birds, right? They're called boids. So they're defined very simply by a bunch of mechanical parameters, a bunch of kind of dynamic parameters, where they're going, how fast they're going, and then a collection of behaviors. And the behavior is nothing more than a function to return effectively a numeric type. In this case, it's a force vector. And so a boid can have any number of behaviors attached to it. Every one of those behaviors takes all the mechanical parameters and takes its surroundings and calculates some force vector, and then we sum up the force vectors over the behaviors. The three classical behaviors to achieve sort of flocking behavior are separation, alignment, and cohesion. So in separation, for all three of these behaviors, you look kind of around you and you see what boids are near you. Separation keeps you a certain amount away from them with a force. Alignment steers you towards the average direction of your neighbors, and cohesion sort of works slightly opposite to separation. It doesn't let you get too far out of whack with your neighbors. Given these three simple behaviors that compose using just that force vector, you get emergent flocking behavior of boids. And we can layer on more behaviors. So we can imagine any number of behaviors to layer on here. One of these could be, the boid's moving with a certain velocity. We can extrapolate its bounding box proportional to that velocity. We can intersect that bounding box with scene objects, and we can apply a force perpendicular to the direction of travel if we know that there's going to be a collision, and this allows the boid to avoid collisions. Very simple function interface, just takes the world parameters and returns a single thing, a force vector. But it's the composability of that force vector that unlocks this very complex emergent behavior. And this has been used for more things than just graphical flocking boids. It's been used for crowd simulations, optimization problems, automatic programming of internet radio stations, I'm told by Wikipedia. And it's just based on this function that returns, in some sense, a force, a numeric value, an arithmetic value, that can be accumulated and applied. Okay, that was Boolean int. I will speed up a little now. Let's go to a T, a type T, and see how that leads us on. So bool is to int as optional T is to collection of T. Collection is usually vector, I might say vector, but all collections are, in C++ that we have a standard at least, are fairly similar in this way. Optional has another trick up its sleeve though, aside from kind of the bool thing, which is that it can provide, if you have no default value for your composable functions, optional can provide you that default value. So if you want to compose together, typically this happens with things that in some way represent real world values like color. And there's often no good default for the operation you want to compose. Optional can give you that default if one exists for your particular operation. And it works just like this. If the optionals are unengaged, because the optional gives you that value outside of your type, the unengaged optional gives you that default value. And you just don't apply your composition, your combination, if they're unengaged. So if optional is like bool, we get presence or absence of the thing. Then vector is like int. We get to combine quantities. We get to either merge them together or merge them together in some way, maybe concatenate them. Now, this is where a common compositional problem creeps in. And the problem is usually that I mix up the return type of the thing. And it's almost always down to a mixed up return type in some way. Now, I'm putting this up on slides as if our problems are recursive. And you might not think you have many recursive problems, many recursive functions. This is because we've been trained as C++ programmers to think iteratively. Because we think iteration is somehow, I don't know, more natural or faster. But in thinking about composition, I want to make the case that recursive solutions are usually the right place to start thinking in structuring the code and the composition. Even if you later remove the recursion, starting out thinking recursively elucidates the compositional beauty in a way that iterative solutions often make hard to see. So it's the right place to start. But even if we have something like this, what usually we have is something like this. I get confused over what I'm writing. I'm working on that small thing, I don't see the big thing, and I end up writing functions that return all these different things. They might return a collection of things if I'm operating on a branch of a tree. They might return values for different kinds of leaves. They might return a vector of things if there's an array kind of a leaf. And when you're solving any kind of interesting recursive problem, which might involve sort of mutual recursion as well, this tends to crop up. And the telltale signs here, you step back, the code is ugly in some way. The telltale signs are usually that you have sticking out conditions, right? Oh, there's a special case in this function that I need to deal with if it's A or B, right? Or bits of shim code to shove things in containers and get things out of containers. This sort of thing tends to happen. And I find the solution to that is trying to write functions whose parameter types are the same as, or whose return type is the same as one of their parameter types. And that makes it a little bit more composable. Lining up these types is the easiest way to composition, and failing to do that is when I get all those uglinesses in the code. So kind of the mantra here is, when I'm working with a container, I try to stay in the container. If I'm working in a vector, I write my function to take a vector. If I'm working with an optional, I write my functions to take an optional. Because there's always a cost to coming out of container world. There's always that condition there. You have to check whether an optional is engaged. You have to check whether a vector is empty. You have to wait for a future to materialize. So when you're in a container, stay in the container. That's a good tip for composable code. So composable functions stem directly from the composable properties of their return types. Bool is the simplest, and or. And then we move up to numbers with arithmetic and ordering operations and things like that. And finally, we move up to collections where we concatenate them or merge them. And in some sense, it's all sort of turtles all the way down. You can have collections of numbers, et cetera, et cetera. And functions that take the same types as they return in some way unlock that ability to feed back and get that kind of composition. So these are the basics of type level and function level composition. And these lead directly to almost all composability when we move up to objects and patterns. So the next rung on the ladder here is object level composability. Now let's imagine again that we have some interface. And again, I'm using plain old object-oriented, old-style virtual functions, you might think, because this is, there are millions of lines of C++ out there, which is exactly like this. So the question that arises is, let's say we've thought up an interface that we want. How do we know that this is a composable interface? How do we know this is going to work out? What classes should we write to this interface? And the first class I always try to write is the zero class. The class that does nothing, but does it composably. So this is the logger that accepts an entry and does nothing, produces no log. This is the allocator that always returns null pointer. This is the parser or the validator that always fails. Or the visitor that uses the identity operation. Or a request that does nothing, or an async task that finishes immediately, or maybe finishes never. Those are both possibilities for a zero object. So I try and write this object. And if I can't write this object, it's a really good sign that my composability abstraction has gone wrong somewhere. And possible problems that usually occur are that maybe there's no default state. Maybe I'm trying to default construct something inside and it just doesn't work. Maybe I've coupled together state with actions in some way. Maybe I've got some side effectful behavior in there that I need to factor out. And like I said, maybe I'm doing this world switching thing. Maybe I've got shim functions in there that take things out of containers and put them into containers, and I'm not staying in the container world. So a few solutions. Sometimes, make sure I'm using composable types, applying regular solid principles, avoiding world switching. Like I said, if I'm in a container, I try and stay in the container. Sometimes I just need to step back, find a better abstraction. The second object that I try to write, assuming the first object went fine, is the pass-through object, right? When we're talking about objects and patterns, this is sort of the second really important one to try. The object that assumes another object exists lower down and delegates to it in some way. And the pass-through object that passes through everything without looking at it isn't very interesting. So usually it's the object that makes some kind of choice about which object to delegate to. Now, this is where I get to reference Andre's talk. Stood allocator is to allocation, what stood vector is to vexation. If you haven't seen this talk, it's a masterclass in composability. It's ostensibly about allocators, but really it's about composability. So Andre presents, very simplified on my slide, but Andre presents an allocator interface, and it returns a block, and the block contains a pointer and a size. Now, the pointer here, guess what the pointer is? It's doing the job of bool. A null pointer or a non-null pointer is exactly like a bool, false or true. The pointer is valid or it isn't. And with just this interface, Andre is able to create a bunch of different allocators. Now, some of them are just sort of allocator mechanical type things, but a really important one is the fallback allocator. That's what powers the whole composition, really. It is that delegation object, that if-else object. Bunch of other allocators that Andre shows, so stack, fixed size, slab, etc., etc. And finally, delegating to the mallocator. By the way, if you watch this talk, you will notice the similarity here to the chain of responsibility pattern, because it's exactly that, leveraging that bool, which is really a pointer in the block, in the allocator pattern. So, yeah, compositions of all of the above, powered by the fallback allocator. This is the second object that I tried to write, right? And like I say, bool is very humble and very simple and even trivial, but it powers 50% of everything in the world. I don't know, something like that. So, yeah, the pointer here inside the block is doing the job of bool in the composition pattern. Now, these days, when Andre gave that talk, he presented sort of this binary choice. I might often try to extend that to a n-ary choice with variadic templates. And this is a pattern I might choose to do that. So there's a fold expression over or here. That's giving us that short-circuiting, that chain of responsibility pattern in one line of code there in C++. And as I was watching Herb's talk this morning, it struck me that this pattern, so as you can see in this pattern, because a pointer isn't really a bool, we're filling in the block using this lambda later on to use it as if it were, the lambda returns the bool, but what we really want, we don't want the bool conversion because we don't want to lose the block. And so we've got the block outside of the lambda. So at the moment, this pattern is useful for that kind of thing, But I'm wondering if pattern matching might give us a better way to do this in future. There are various ways to achieve this. I haven't code golfed this slide, but yeah. So at this point, I've talked about types. I've talked about objects. Does anyone have any questions at this point? Okay. Well, I'm somewhat...
We've got a question coming in. Can a function throw an exception when it can't do a job and still be composable, like standard map?
Can a function throw an exception and still be composable? Yes, I think so. It boils down to having the pattern of composability encompass the idea of exceptions. I don't think exceptions, functions can fail and still be composable. The type of failure might be an exception. I don't think that exceptions, as a mechanism, prevent composability here. So, I'm somewhat known for being a functional programming geek. And functional programming can be a little bit polarizing in C++ because, and I've deliberately tried to make this talk use sort of regular C++, because a lot of people see, code like this, and they say, who writes this? All the code I see in my day job is 2000s era, object-oriented, it's nothing like this. But the point of this talk in some sense is that we all write code like this, because it doesn't matter what paradigm you're using. It doesn't matter that you're using object orientation versus functional programming. It doesn't matter if you're composing functions directly or indirectly, because object interfaces are functions, collections of functions. These same principles underlie our code, no matter how we write the code. So it makes sense to recognize them, So I've heard folks say, I just want to write regular code. I don't want to use insert functional pattern here. To me, that sort of misses the point, because you're using them whether you like it or not, right? I'm using them whether I recognize them or not. And all I'm trying to do is recognize them so that I can know more about my code. Composability comes directly from operations on types being composable through functions being composable up to the level of objects and higher level structures. So talking of objects and patterns, the poster child for composable patterns is, strangely enough, Composite. And in the Gang of Four book, this is what it says. It says, Composite lets clients treat individual objects and compositions of objects uniformly. So in classical style, and indeed in the Gang of Four book, which is now 26 years old, I think, it was 1995. So in that object-oriented style, it's a bit of a clumsy pattern, to be honest, because the interface, as you can see here, tends to get a little bit bloated. It has to contain all the functions for dealing with leaf objects, as well as the functions for dealing with collections. And that's kind of a bit of a boilerplate. But the important thing about Composite is that the sort of functional interface of the leaf class is the same as that of the collection. You can call draw on leaves, you can call draw on collections. So, saying that another way, we might say, what makes that useful? What makes it useful is that you don't have to have that condition in the handling code, right? You don't have to think about that dichotomy between a leaf or a collection at the calling code. You just call draw. You can write functions against one interface, and it works for the whole hierarchy, the whole composite. So, what's the real learning here? What makes Composite nice to use? It's that you don't have to put conditions in the calling code, right? Conditions are those things that make your code look ugly when you step back. You worked on the small part, you step back, look at the large part, and you see conditions everywhere, you know something is wrong. So here's the learning that I take away from that. and I'm cribbing from Sean a bit, no raw conditions, right? What is this telling me? A raw condition is any binary condition that doesn't serve one of two purposes. Now, one purpose is intrinsic optionality that's inside a data type, like optional. There's clearly a condition in there, right? There is a dichotomy inside that data type. But above that, I don't want any conditions. The second type of condition is like giving a choice to a user at the highest level possible, like a configuration or construction time choice. I'm at the point now when I write code where if I write an if statement, it's like a slap in the face. It makes me think, really? Do I really need to spend an if statement here? Sometimes I do, because I just have to accept, like all of us, that maybe I don't have time to refactor this today, That clearly there is something wrong here. There is a sign that the architecture is somehow not right. It's always that little bit ugly. Sometimes you have to live with it. But an if statement in the middle of code, like I say, to me it's a thing that really sticks out these days. So, just briefly to take an aside, how many people have seen C++ seasoning? Many folks, many folks. So everyone remembers of these folks, I expect, no raw loops, right? It's a mantra. I'd like to point out that that talk is actually 80 minutes long, and Sean's pretty much done with talking about algorithms after 30 minutes. And in the rest of the talk, he talks about composability of various kinds. So you should definitely go back and watch that talk if you just remember no raw loops. So yeah, here's another way to put it. If statements should occur either at the top of the stack, where they're built into data structure, where they're representing configuration, or at the bottom of the stack, where they're built into a data structure.
Are concepts a way to achieve type-safe composability, or are they orthogonal?
Concepts are definitely a way to ensure that types adhere to interfaces. So they're definitely a useful tool in the composability arsenal. I don't think any one thing is a way to achieve composability, but it's about, it's about matching up types and matching up the ability, therefore, to call functions and to use objects and to use interfaces. And so objects are a key part of that, yes. Very useful tool. Okay, so to me, the secret of composition is when we have uniformity across the type space. We have functions, interfaces that take and return the same types, and when we bake conditions into the types like optional. And this is what enables composition at the object level. And this is nothing new really. This is already good object-oriented style. Object orientation tells us, tell, don't ask. That means don't put the condition at the calling site, have the object embody that condition, right, among other things. So well-behaved functions look something like this. And one of the points about this slide is it's in some sense okay to expand, so it's okay to go from bool to int, or from T to collection of T. The expansion is generally a lot less problematic than the other way. So we can go from narrower thing to wider thing. But it's when we try and go the other way that we find problems. This is where those pesky conditions come in. This is where I have to check that the optional is engaged, or the vector is not empty, or the int is 0 or 1 as opposed to 17 or 42. Okay. So far, everything I've talked about has been like object orientation, function level, type level, runtime. I want to take a bit of a compile time interlude because the same principles apply, perhaps even more so when we're working in type space. It may or may not surprise you to know that I do a lot of compile time programming, and that involves a lot of things like type list manipulation. So in compile time programming, values become types, and pretty much the one collection that is used over and over again is the type list. And the most common problem I see in my code that has to do stuff like this is caused by dichotomies pervading the code, typically between type or type list. And overwhelmingly, the solution that I see used to deal with that is const expr if. So, problematic functions in type space look like this. Here is a type function that takes a collection of t's, and it's returning a t. These kind of formulations are a bit harder to spot in type space because template syntax is, much more involved than runtime syntax. And we're only slowly getting some of the tools we need. But I see these kind of things, if I saw this in a code review, or if I saw this as I was writing the code, if this was evolving in my code, I would, immediately think, wow, I should refactor this. It sticks out like a sore thumb, We know spaghetti code. So I see things like this, and people say, well, at least it's better than Svine. And I say, is it? I don't think it is. I don't think it is. This is, we don't have this. Sorry, Jody? Okay. I don't think we've developed all the compile time tools yet, like the tools we have in kind of classical OO style and runtime. We haven't developed everything we need to encapsulate these kind of things in behaviors. Now, why is this important? Well, I think it's important because reflection is coming, right? I hope, eventually. We're going to get a lot of meta functions in reflection, and in particular, we're going to get a lot of meta functions that build on these kind of general forms where we take a struct and we get the members of it, right? And we do something to the members of it at compile time. And, this is ripe for all the problems of like world switching, like those dichotomies of like, oh, what if it's an int versus a type list? The same principles apply. Write the well-behaved function signatures. Avoid the problematic ones. When you're working with a collection, keep working with collections. We are also, in reflection, going to get things like this. So, as well as sort of that linear composability, we're likely to get a lot of things that do things to members of struct recursively, because you can put structs inside structs. So what should this function return? This is back to the sort of recursion thought. This kind of question speaks to me the heart of what it means to be composable. This is going to be recursion over a heterogeneous structure, struct containing regular sort of fundamental types, but also maybe structs. And so we're going to be recursing at compile time over heterogeneous structures. So this leads me to the last part of my talk. We've looked at type level composability, how that leads through functions, how that leads to objects and patterns, and I think eventually how that leads to higher level structures and hierarchies. So here is the composite pattern. Again, we've got, at any level we can put either a leaf or a composite, a collection, and we can call draw at the top level. So what's the problem here? This works fine, right? What is the problem? Well, there are a couple of problems. One is that, this is an object-oriented pattern, and object orientation makes it easy to do some things and hard to do others. So, in particular, we have an abstract-based class that specifies an interface. We can easily derive a class from that, implement that interface. We can do that any number of times. New leaf types, new collection types, it's all good. We make that interface. It all works as long as we want to draw things, right? The instant we want to find the bounding box of something, for example, we've got this sea of objects, and we need to go plumb. If we want to add the capability to make the bounding box, we need to plumb that through all the objects, right? And we might not even own all the objects. This is known as the expression problem, right? It's half of the expression problem. In other words, object-oriented languages make it very easy to add classes, add types, add objects. Difficult to add functionality, right? Difficult to add member functions because you need to thread them through everywhere. The flip side of that is that typically functional languages have it the other way around, right? Because adding a function is easy. Adding a type involves finding all the functions and finding all the pattern matches and adding your type to that pattern, to those pattern matches. So there's kind of, this is a fundamental problem, the expression problem. I wouldn't advise looking at it on Wikipedia. You can find it on Wikipedia. You can read everything that will be correct, and you'll come away none the wiser. And what solves this problem in classical object orientation is the visitor pattern, right? The visitor pattern solves the expression problem. Well, flips from one paradigm to the other. It's kind of misunderstood. It's not really about visiting, but it is about taking the one case of affairs where it's easy to add types, hard to add functionality, and flipping it to the other side where it's easier to add functionality. You can add a new visitor, that represents some functionality. But with the visitor pattern, it's harder to add types. So as Bob Nystrom said in his recent book, which by the way is really excellent, Crafting Interpreters, visitor patterns about approximating the functional style in an OO language. Right, so this slide says what I just told you. Object orientation makes it easy to add types, hard to add functions. Functional type stuff makes it easy to add functions, hard to add types. So the expression problem is kind of fundamental. It's not going away. There is no solution that makes it easy in both camps. But we get to choose which kind of camp to be in depending on the grain of the problem. Composition is about something a little deeper. And what we want to do here is try to separate the computation from the traversal of the hierarchy. This is what composition is about when we're talking about higher level structures and hierarchies. Well, now this is C++. When our structures are flat, we're already great at separating computation and traversal because Alex Stepanov taught us how to do that, right? The STL algorithms do this in spades. We've got iterators. They apply to every kind of flat structure you could think about. And they do exactly this. They separate computation and traversal. But they do it through that iterator interface, right? So they only work on flat structures, right? On linear structures. And if we're talking about hierarchical computation, we're much less good at that. I'm much less good at that. It takes real effort to separate computation from traversal in a hierarchical data structure. So I just want to go through with you a consideration of how we might do that in one case. This is a rose tree. If you haven't heard the term before, it's a tree where it has leaves, of course, at the base. At any node, it can have any number of subtrees off that node. So it's, a binary tree would just be 2 subtrees, or a KD tree would be K subtrees. But a rose tree is a variable number of subtrees from any node. And this is about the simplest, this is about the fewest number of lines I could fit on the slide to express that in C++. So it's a variant of either T, which is the thing at the leaf, or a vector of subtrees. And this actually does work because vector doesn't need its value type to be complete at the declaration time. So if we have a rose tree containing strings and we want to, sum up all of the string lengths, find the total length, this would be a typical way to write that function given the code I just showed you on the slide before. If you haven't seen overloaded before, it was proposed at one time. It basically is a type that inherits from the lambdas and provides that function call. So you get basically an overload set from these lambdas. So we're visiting the tree. It's a variant of T's and vectors. In the case it's a T, we just size the leaf. In the case it's a vector, we transform reduce it, sizing each subtree. Seems straightforward. But what's wrong here is that we've mixed up concerns. This function does both the traversal of the tree and it has baked into it knowledge of the operation. It says size right there. It says std plus right there. That's the operation that we're doing on the leaf and the node, but it's mixed up in the hierarchy, in the traversal. So what we want to do here is separate the what from the where, right? And like I said, this is already done for us in many STL algorithms. They work on flat structures. It helps to think about doing the same thing with hierarchical structures. So here's one way we could do the where. We could pass in the what as functions, right? So notice the signature of this function. It looks very, very similar to transform reduce, because fundamentally what it's doing is transform reduce, just not on a linear structure, on a hierarchical structure. But we pass in, just like in transform reduce, we would pass in the transform operation, which here is the leaf, the TOP, and we'd pass in the reduce operation, which here is the sort of branch operation. Now, this function embodies the traversal of the tree without encoding the what we're doing to each locus on the tree. Now, we're used to the STL algorithms, and iterators are a fantastic abstraction. And what iterators do is turn all of the flat structures into the same kind of thing, right, for the algorithms to work on. When it comes to hierarchical structures, we don't have that nicety. And so if you have different kinds of hierarchies, it's beyond the scope of this talk to try and present a hierarchy independent traversal. We don't notice that the traversal is different for each data structure in the STL because of the iterator interface. But when it comes to hierarchies, we might want to make this particular thing could be different for each kind of tree. It's a very interesting thing to think about, but it's a bit beyond the scope of this talk. But the point here is that we separate the what from the where. And here's the what, right? So the call just looks like this now. We're saying exactly what we want to do. When there's a branch, we want to use plus and 0. When there's a leaf, we want to use size. Now, if you're really paying attention, you might notice this is still slightly mixed up. And the reason it's slightly mixed up is that we're still actually using a vector inside the rows tree. And so that requires us to sort of switch worlds into vector. And so that's why, there's not a complete symmetry between, it's not just two functions, it's actually the leaf function and then two things to deal with the vector, the 0 and the plus, right? And that's because the vector is itself not specified in this kind of functional way. But, separating the what from the where in a hierarchical structure gives us that composition, gives us that kind of nice feeling of this is exactly what we want to say and nothing that we don't want to say. So, iterators are great, they decouple, and ranges are great. They decouple algorithms from data structures, but fundamentally in C++, we live in Flatland, right? And in fact, most things are not flat. And that sounds weird to say because most things in C++ are flat, but they are that way because we think that way, because we've been trained to think that way. Like, if there's one area where C++ standard is really deficient, I would say it's graph algorithms. Graphs are not flat, but they are ubiquitous and applicable to just about every problem in the world, as far as I can tell. But we just don't have them in C++. We have Flatland. But the point is that, lifting ourselves into higher dimensions gives us an insight into Flatland, and it leads to that same kind of composability. So, I said the rose tree example was a bit wonky because we had vector inside it. In a functional language, if C++ were a functional language, vector would look like this. This doesn't work in C++ because pair does require its types to be complete. But, this is what reduce looks like in the standard, just through a different lens. We've got the init value is really how to treat the nil part of the variant, and the operation is how to treat the variant which has t's and some more t's, head and tail. You might notice also that this is a right fold. It's equivalent to a right fold, which is just an interesting thing to note. And it sort of gives us an idea about why right folds are very important, especially because we could make this lazy in the fold. Anyway, so the point here is that we're trained to think of things iteratively, but thinking about things recursively, and in particular in higher dimensions, really unlocks that structural composition for me, and separating what from where. Now we're almost at time, but I have a further rabbit hole to suggest that you go down, which is separating the when from the what and the where. And the when is hard to spot because there's no syntax for it, but it's in the function call. It's the syntax for function call, right? That's the place where the when happens, and that's the realm now of structured concurrency and executors and all that good stuff. And like I say, it's a rabbit hole. I encourage you to think about that in terms of the separation at your leisure, but I don't have time to talk to you about it today. So in the end, why is any of this important? Well, it's where I started. Alice writes code, gives it to Bob. Bob uses it for something Alice didn't need to think about, but it still works, right? And the reason it works is because Alice wrote the code with a principled approach to composability. This is all of programming. Beautiful composition comes directly from the properties that we recognize on types, on functions, on objects, on patterns, that are leveraged through the code from the lowest level up to the highest level. And it isn't something that we can TDD. You won't find it in any requirements document. None of our customers are going to ask for our code to be composable. They're just going to ask for it to do the thing they want. This is something we have to do for ourselves. But it is something that we all, including our customers, will benefit massively from. So, thank you very much.
We have 2 questions from online. And it's kind of going back to the earlier part of your talk.
Mm-hmm.
Is the zero object essentially just the identity object of the given user-defined type? To put another way, is an operation required to be defined for the user-defined type to know that something is the zero object?
The operation, yes. The zero object is more about behavior than identity, I would say, when we're talking about composition. So the operation might be one of several different operations, and what's important about the zero object is that it does that operation, but it does it composably.
And then, are you saying that reduce in MapReduce is a problem for composition because it narrows from container T to T?
Yes. Well, it depends where you want to end up, right? If what you want to do is reduce the thing and that's your computation, fine, reduce the thing. But if you want to then feed that forward into more computations, it often makes more sense to, map. The map of MapReduce is exactly when in the collection, stay in the collection. And the reduce is more of a focused computation of what you actually want to get out, right? It's at the end of the chain is the reduce. All right, thank you all.